Right, so we're still talking about linear functions. This video is going to focus in on how can I find rate of change from a table, and if I find a rate of change, then I know that I have a linear function. Because if I don't have a constant rate of change, then I don't have a linear function. So we're not going to have to graph using our tables. We can find this just by looking at the tables. So remember that rate of change is slope. So when we're talking about rate of change, we're looking at the change in our output, or y. So change in output, or we can put up here y, over the change in our input, or in other words, our x value. So basically y minus y over x minus x. And so the easy way we can do this, because we have to make sure that it's constant between all of our points. We don't have a linear function if from one set of points to the next set of points it's not the same. So I always start with my input, and even though maybe all of these in our examples are the same, you have to keep in mind at any time our input values could count by different numbers as well. So from 1 to 2, we're adding 1, right? That's a difference of 1. From 2 to 3, so 3 minus 2 is 1. We always go from the highest number to the smallest. So 4 minus 3 is, again, a difference of 1. And 5 minus 4 is a difference of 1. So I know at least my inputs are all changing the same. So now I look at my outputs. From 5 to 8, we're adding 3. So another way we could find that is doing 8 minus 5. So again, I could do 11 minus 8, or I just know that 8 plus 3 gives me 11. And from 11 to 14, again, is plus 3. And from 14 to 17, again, we added 3. So the difference between each of those is 3. So because our rate is constant, our rate of change is constant, this is a linear function. So yes, and it is because the rate of change, ROC, is constant. And because we could have a constant rate of change and for some reason have the inputs not be changing like they should. So our rate of change is constant and each input has exactly one output. And that's important because that tells us that that's a function, right? That we have a function. So yes, because the rate of change is constant and each input has exactly one output, this is a linear function. Now, our rate of change is going to be our change in our output, so our change in y was 3, over our change in x, which is 1, and so 3 over 1 equals 3. So our slope, our rate of change, is 3. Alright, so here we have a couple more tables. And so we're trying to decide, does the relation defined by each table represent a linear function? And then explain why. So again, I always start with the input. Those are pretty easy. From 0 to 1, that's a difference of 1. I add 1 to get from 1 to 2, and I add 1 to get from 2 to 3, and I add 1 to get from 3 to 4. So that's a good start. From 2 to 4, I'm going to add 2. From 4 to 7, we're going to add 3. From 7 to 8, we're adding 1. And from 8 to 10, we're adding 2. So when I look at this, our rate of change is not the same because our numbers on both sides, for both our x and our y, should be the same. And it's not. And because of that, so like for these first 2 points, we've got a rate of change of 2 over 1, but then For our next set of 2 points, we have a rate of change for 3 over 1, and then we have a rate of change of 1 over 1. So see how those aren't the same. And so this is, so our rate of change, our explanation, our rate of change is not constant. Therefore, this is not a linear function. So again, I need those numbers to match on both sides. They match the x values, that's great, but we didn't match on the y values, so that's why it's not a linear function. So now let's try our second example here. So from 0 to 3, we have a difference of 3. 3 to 6, we have a difference of 3. 6 to 9, again, we're increasing by 3. And 9 to 12, we're increasing by 3. So now we just have to look at our outputs. Our inputs look good. Again, we have all the same, so that's a good sign. So from 0 to 1, that's a difference of 1. From 1 to 3, that's a difference of 2. From 3 to 6, we have a difference of 3. And from 6 to 10, we have a difference of 4. And so now we're looking at it and we're like, again, our outputs don't have the same rate of change. And so our rate of change is not constant. Therefore, this is not a linear function. My question to you, are these functions though? So if you could email me, I'll give extra credit to whoever can email me and tell me whether in example 2, and you need to tell me 7.3 example 2, and then whether or not these are functions and explain your reasoning, and I'll give you some extra credit. So, extra credit option, tell me in 7.3 example 2 whether the two tables are functions or not, and explain why. Alright, so our last example, example 3, we've got our word problem. And so when a scuba diver goes underwater, the weight of the water puts pressure on the diver. Sorry for that typo. The table shows how the water's pressure on the diver increases as the diver's depth increases. So our first thing is, what is the rate of change of this linear function? So it's already telling us it is a linear function. And then we're going to talk about what that rate of change represents. So like before, we're just going to find this difference. So 10 to 20 is a difference of 10, 20 to 30, again, difference of 10, and 30 to 40, a difference of 10. And so then we need to find the difference over here. So I would do 8.8 minus 4.4, which will give us 4.4. And then if I do 13.2 minus 8.8, I'm going to get 4.4. And if I do 17.6 minus 13.2, I'm going to get 4.4. So right now I have a rate of, they're the same on both sides. So we, of course, it told us we have a linear function. Our rate of change is going to be 4.4 over 10. And so what that represents is that the pressure, helps if I could spell today, the pressure on the diver increases 4.4 pounds per square inch for every 10 feet they dive. Oops. So that's what it represents. So for every 10 feet they go down, the pressure increases by 4.4 pounds per square inch. Now, we're going to use that rate of change to predict the water pressure on the diver at a depth of 60 feet and at a depth of 100 feet. And I kind of wrote in front of where I was going. But I know by increasing every 10, I increase every 4.4 over here. So at 50 feet, I would take 17.6 plus 4.4, and I'm going to get 22.0. I'm going to skip down here to 60 feet. I'm going to add another 4.4, so we're going to end up with 26.4. And so that I can now answer this first one, 60 feet. So at 60 feet, the pressure is 26.4 pounds per square inch. Alright, so I've got my 60 feet. And then I can go 70. I'm going to add 4.4. And so I'm going to get 30.8. And add another 10 feet. So at 80 feet, add another 4. And so we're going to be at 35.2. And at 90 feet, we increase to 39.6. And then at 100 feet, the pressure is 44.0. And so that's the last one, depth of 100 feet. So the water pressure, thank you, at 100 feet, the pressure is 44 pounds per inch squared. Now, some of you are probably going, well, Mrs. Cartwright, really, if we just use the equation y equals 4.4x, we wouldn't have had to complete the table that far. You're right, and you're more than welcome to, if you can figure out the equation, use the equation in order to solve, because that was part of 7.2, was being able to write equations, and so that would be our equation. And that ends 7.3.